Good evening, everyone. Welcome to the week 7 problem-solving session of Matlab-Based Programming Lab in Chemical Engineering. Let's wait for like 2 more minutes so that if there are more people to join, we'll wait for them. And we'll start the session by like 2 minutes. So let's begin today's session. So this week we'll be discussing CSTR in series. Two CSTRs will be given in series. So here we are trying to study a first order chemical reaction where A is forming B and it takes place in two CSTRs which are connected in series. The contents in the two CSTRs are well mixed, but the reactors are not at steady state, which means like right on the previous session, like I'll just show you that also right now. So we had studied this system last week, which was where we studied the temperature. How is the temperature varying for the solid body with respect to, and we have a reservoir temperature which was kept as constant. But this system was at a steady state. Okay. So right now, what we are trying to do is we are not looking at a steady state reaction. Instead, we are looking at the beginning of like what happens when your CSTR is just about to, the reaction is just a beginning. So then what happens is before reaching the steady state, there is an unsteady state. That is the concentration of both A and B varies in this both reactors with respect to time. So once it has evolved with respect to time and then it reaches an equilibrium concentration, that is A and B reaches an equilibrium concentration and then it remains as such. Okay, so then that is called as a steady state. Then it does not vary with respect to time. So here we are trying to study the evolution of A and B with respect to time. Now, these are the equations that we are governing the system. So one refers to the reactor 1, that is this reactor. This is reactor 1, and this is reactor 2. We have both A and B in both reactors. So this is the rate of reaction, it's the concentration change in reactor 1 for the element A. So here we have 1 by 2. So this is 1 by 2. This accounts for the flow rate. And then Ca0 minus Ca1. Ca0 is what is coming inside. So this has A0. And what is going outside the reactor, that is Ca1. So this refers to the flow of the reactor. And then you have, since there is a reaction that is happening in the system, you have this A that is converting into B. So that reaction is given as minus KCA1. Now coming to the CB1, you have what happens is since A is reacting, you have the B that is forming. And also you know that there is no, in the inlet before the reaction, there is zero B. The B element is not there. So only in the outlet you will have the B. So that is what is there. You don't have B0, you only have B1. So that is 1 by 2 CB1 is there, whatever the concentration of B in the outlet of the area of the first reactor. Okay, so that is CB1. And then whatever is formed from the reaction that A has converted to B, and that accounts here. That is KCA1. Now this is your second reactor. That is A2, B2 refers to the concentration of A and B respectively in the reactor number 2. So this is the reactor number 2. Here in the inlet you have both B and A, and also in the outlet you have both A, B and A. So if you're looking at the change in concentration of A in the reactor 2, this accounts to the flow. That is CA1, that is the inlet, and CA2 is the outlet. And then you have again a reaction happening, that is A converting into B. And when you account for that, this will be the reaction equation, that is minus KCA2. Now this is the concentration change of B in the reactor 2. Then we have again the inlet and outlet, as I said. Here in the inlet and outlet, both will have a B constant. B will be there. So we have the inlet minus the outlet. And then whatever is formed from the reaction, from the first order reaction, you will have A converting into B. So that amount is accounted here. That is KCA2. So these are the 4 reactions that we are trying to study here. Now, so this is what is given here. Ca0 is a concentration of A in the inlet of the first reactor. That is whatever is here. Cb0 is not there because A has to convert to B. Only then B will be there. Now, Ca1 is a concentration of A in the outlet of the first reactor. Ca2 is the concentration of A in the outlet of the second reactor. So here you have Ca1, here you have Ca2. And again, Cb1 is a concentration of B in the outlet of the first reactor. So here you have Cb1 and here you have Cb2. K is the reaction rate constant and tau is the space time of each reactor. So here both tau's here. Right now we are considering both the reactors are having the same space time. So that is why we are using a single tau. Okay, everywhere you are using a single tau. It's not tau 1, tau 2. There is only one single space time for both the reactors. Now we have several problem statements that we are encountering here. The first question is, determine the evolution of concentration of A and B in both the reactors during the first 10 minutes of the operation. So that is, you know that the first 10 minutes of operation reaction might have reached a steady state or it might be still evolving. Then you will have to identify how is the A and B concentrations changing in the first 10 minutes. And next question is, determine the time requirement for the system to reach steady state. So after maybe within 10 minutes it might happen, or even after 10 minutes the reaction might keep on evolving. And finally it reaches steady state. So here we have to account for the time that is taken for reaching the steady state. And the third part is study the effect of space, time, and rate constant on the time required to reach the steady state. So we have to identify what is the effect of space, time, and the rate constant there. So now we have some initial conditions that is given to us, that is Ca0. That is to begin the reaction. Your initial concentration of Ca is 20 mole per liter. Your K is given as 0.12 per meter, and tau, that is the space time, is given as 5 minutes. Okay. Now here we have different categories that is clubbed together. So first one is, if you see this equation, this is an ordinary differential equation. It's an ODE. This is not a PDE. Why? Because we only have a single independent variable. And here that single independent variable is the time. So here it is, this whole equation only has one independent variable, which is time. And so hence it is called as ordinary differential equation, not a partial differential equation. So that's the first part. The next is you have algebraic equation. So sorry, then we have initial value problem. That is, we have the initial concentration of Ca0, Ca1, Cb1, Ca2, Cb2. These things are unknown to us. So only the initial condition of the system is given to us, which makes it an initial value problem. Next, we have coupled equations. That is, last time we have seen ordinary differential equations, but in that we only had one single equation to solve, right? But here you have like multiple equations. You have the multiple equations here, and these are coupled. Why is this coupled? Because if you look at if you're trying to study the Ca1 concentration, the behavior of Ca1, you can't just independently solve this equation because you have the Ca1 coming in this equation also. And you can't independently solve this equation also because you have Ca1 coming here and Cb1 is there in the this equation, the fourth equation. Okay, so the elements of each of the equations are there. You can see that in multiple places. So because of this, you have a coupled ODE. That is, these four reactions. The four ODEs has to be solved simultaneously. Okay, so that is you have an ODE problem and then an initial value problem, and also these ODEs are coupled. So these are the different categories that we'll be encountering in this question. Now let us come to the first part of the question. Determine the evolution of concentration of A and B in both the reactors during the first 10 minutes of the operation. So before solving that, I'll just do a quick recap. Just give me a second. We have already done this in the last week. I'm just doing a quick recap. When you have an ordinary differential equation, dy by dt is equal to some function. How do you solve it? So you have this MATLAB inbuilt ODE solvers, that is ODE 45, ODE 15, yes, ODE 23. There are several solvers that are available to us. So what is the general syntax of this ODE solver? So general syntax is you have to write the first, okay, we'll come to this later. First, you have to write the keyword, that is ODE 45, and then you open the round brackets, and then what you have is you give the function. What is this function doing? This function should return your left hand side of the equation, sorry, the right hand side of the equation, whatever the ODE equation is. That should be the output of this function. And then you should write to till what should I study? What is a T span I should like? What till what time should I study the behavior of the system? So that is called the T span, which is given in square bracket. Here you give the lower limit and the upper limit. T0 is the starting time, and Tn is the time till which you have to study the how much the system is evolving. And then you have y0. Y0, since we are solving an initial value problem, you have the initial conditions that are listed to us. For example, in our question, we had the CA0 that is given to us. So that forms the initial value here. So here you have, this is the syntax of ODE. Now we have the outputs, that is for several time intervals that is ranging from T0 to Tn, you will have the respective Y solution. That is here in our case, for several time, that is from, if you're studying to 0 to 10 minutes, you will have 0 to 10 minutes, it will be divided into some intervals. And corresponding to that, you will be getting CA1, CA2, CB1, CB2, the four concentrations. So that will be forming your Y solve. So again, repeating, f name is a function that returns dy is equal to f of ty. T0 and y0 are the initial conditions such that the y at T0 is equal to y0. Now the Tn is a final value until which we need the solution is decided. And also I had told you there are several ODE solvers, and these ODE solvers have some underlying mathematics behind it. So here the ODE 45 is based on Tangakutta fourth order method. Another thing that you have to remember is that in ODE, what happens is you can only give the initial and the final value, okay? And the intervals at which the ODE solver is solving is dependent on the solver itself. So it uses adaptive step size. That is, if you are entering 0 to 10 minutes, it is not guaranteed that your T solve will be at equal intervals. You can't say that it will be 0, 1, 2, 3, 4, 5. Like it will not be at equal intervals. Instead, it will have adaptive step size, which is determined by the solver, okay, to maintain the stability. So if you need if you need at constant intervals, there is some modifications you have to do in the later stage after solving the ODE, which we'll come to that later. We had seen some examples. This you can see the last recordings to understand how these examples are solved. Now coming into the several ODEs, we had discussed of ODE 45. This is a solver of popular choice, and it is based on non-stiff problems. And we have also discussed what is stiff problems and non-stiff problems. Last week I already said that stiff and non-stiff, this comes when you have like coupled equations, okay, coupled ODEs. In coupled ODEs, what happens is, right now you have like four equations, one governing CA1, another governing CA2, CB1, and CB2. What if CA1 is rapidly changing compared to CA2? Okay, so when your variables are having different behavior with respect to time, then you call that system to be a stiff problem. If all your variables, that is CA1, CA2, CB2, CB1, is all varying, like almost in a similar pattern with respect to time, then it forms a non-stiff problem. So ODE 45 is generally used when we are dealing with a non-stiff problem, and it uses adaptive step size to approximate the solution or to the ODE. Then you have ODE 23. It is similar to ODE 45, but uses a simpler algorithm, and it does not have high accuracy. Okay. Next is ODE 113. It is also suitable for non-stiff problems, but it uses variable order and variable step size method. And the highlight is it is having a higher accuracy than ODE 45. Then we have ODE 15. Yes. Whenever this S comes, the small letter S, this denotes that the solver is used for solving stiff problems. It also has variable order, variable step size, and it is based on backward differentiation formulas. So this is the max behind it. I already said this, and now we can say that stiff problems can be more difficult to solve numerically because traditional numerical methods may require very small time steps to achieve the stable and accurate solution. In contrast, non-stiff problems are relatively easier to solve and it can be solved even with a larger step sizes with good accuracy. I hope that part is clear. That was a quick recap of how do you solve the ODE problems. Now let me just keep sharing the previous one. Okay. So let us try to do the first part of the question, that is determine the evolution of concentration A and B in during the first 10 minutes of the operation. So for that, I'll just share MATLAB quickly, just a second. So this is how the code is being written. You can see the same code in your recording lectures also. I'm just doing a quick recap so that in case you have doubts in any of the portion, you can just stop me and ask the question. So now is first we have the ODE solver here. The ODE solver, it calls in a function which has to output your ODE equations. So that function is called a CSTR. And this is a time span I'm intending to. So in the question, it has been asked that how will the system evolve for 10 minutes? So 0 to 10 minutes. And your initial values. So initial concentration values, it's all 0, 0, 0, zeros. Okay. Now coming into the like, so after getting this T-sol and corresponding C-sol, you have the plotting equation. We'll come to that. Before that, let me just show you the CSTR equation. So the CSTR equation, what happens is, this is a function. Okay, it outputs a certain DC. I'll tell you what this DC is equal to CSTR. It takes in two input, the T and corresponding C's. Now what happens, C is a vector. It has four elements. The first element corresponds to CA1, second element corresponds to CB1, third element corresponds to CA2, and the fourth element corresponds to CB2. So that is first two is for reactor 1, and the next two is for reactor 2. This you have to keep in mind. Okay. Next is all the constants that has been given to us in the question. That is K is equal to 0.12. That K constant has been given to you. Now tau, that is tau value, that's the space time is given as 5. And then you have CA0, that is initially when the system is starting, what is the concentration of A? CA0 is given as 20. So we have all those factors. Now you write the equations. So this also I've given a small example in the previous week. I'll just quickly tell you. If you have like multiple ODEs, what happens? You stack this multiple ODEs to form a column. It's a single column. You try to add all this. So that is DC is a column vector. In that column vector, the first entry, that is the first row corresponds to your first equation. That is corresponding to DCA1 by DT. That is whatever change. This DCA1, you had a equation, right? So that corresponds to the first element in your column. The second element corresponds to B1, CB1. Okay. And the third element corresponds to the equation corresponding to CA2. And the fourth element corresponds to the equation related to CB2. So you stack all your multiple ODEs into a column vector. How do you know it's a column vector? So this is a row number. So row numbers, you can see it is varying from 1, 2, 3, 4. And you can see all the column numbers is just 1. So this is what you get. If you have multiple ODEs, you should be stacking it into a one single column vector. And each entry of the column, that is each row of the column vector will be corresponding to an ODE equation. And also remember that the variables that you take. So here what happens is, this is an initial guess, okay? In this initial guess, here the ODE order is first equation is CA1, second equation is CB1, third equation is CA2, and the fourth equation is CB2. The same order has to be maintained here. This corresponds to CA1. This corresponds to CA2, CB2, sorry, CA1. This is CB1, CA2, CB2. Okay, this two for the reactor 1 and this two for the reactor 2. So the order of the variables, you shouldn't be mixing it up. You should write it in the right order. Now what is required is you need to plot how the system is behaving, right? So here you have like two systems, that is reactor 1 you have, reactor 2 you have. Both if you want, you can plot it in the same graph, that is completely fine. Right now, what I'm doing is I'm creating two figures, one for reactor one. So this is for reactor one, and next is for reactor two. How do you plot it? For the reactor one, what do you do is you plot the T salt and corresponding what will be the, okay, let me just run this portion. Okay. I'll show you what is happening. I'll just run this portion, say run section. Yeah, you got the T sol and Y sol here. Okay. So T sol is, it ranges from 0, it goes up to 10 minutes. Okay. That is 73 entries are there because it is using adaptive step size. It is not uniform intervals. Next is corresponding C sol. You will have four columns. The first column, you can see the entry of entry. So first row entry is 0, 0, 0. This corresponds to the initial value. Initial value of CA1 is 0, CB1 is 0, CA2 is 0, CB2 is 0. And then you have each column. This first column corresponds to CA1. Second column corresponds to CB1. The third column corresponds to CA2. And the fourth column corresponds to CB2. Okay, so likewise, when you're plotting also, you should keep that in mind, the order. So when I say all rows, first column means I'm corresponding to CA1. And on the same plot, I'm plotting all rows, second row, that is CB1. So this will be the CA1 and CB1. Basically, the concentration changes in reactor 1 will be plotted together in the plot. Again, the second part is I'm taking all rows and third column. What is third column? Third column is CA2. And the fourth column is, that is all rows, fourth column is CB2. And these two plots, I am also plotting it on the same figure. Okay. Now, this first figure will give you reactor 1, second figure will give you reactor 2. Now, let me just run this for you. Yeah. I'm sorry, just a second. We are running it. I think this is right now. So the figure 1 corresponds to the CA and CB concentration, the reactor 1. So if you're trying to analyze how the system is behaving, you have the initial both A and B, it is changing. It is CA1, it's like slowly it is increasing from 0 and it's going higher and higher. And you have your A converting into B. So initially your B concentration is again 0. But as slowly A is trying to react, you will see initially the what is the change in B is very slow. But when this is because of the starting of the reaction. But once the reaction starts properly, then you have the B value also increasing because A converts into B. This has not exactly reached the steady state within 10 minutes, but you can see it is approaching somewhere to the steady state. Steady state means this will be like a flat region. It will be a straight horizontal line, both red and blue. Now coming to the reactor 2 also, you'll see the same behavior. Your A is still higher, okay? And the B is going from 0 to a higher value because your A is getting converted into B. Okay, and still you have your B value is still less than A. But as time progress, you may see that, okay, your A value is decreasing and the B value is going higher. So if you run it for more time, you will be able to see this. Here also in this case, you can see that both A and B hasn't reached a steady state. It has to be like a horizontal line. Okay, that is not happening here. So both A and B hasn't reached a steady state. So this is the first part of the question, that is determine the evolution of concentration of A and B in both the reactor used during the first 10 minutes. So here you have your first reactor, CA1 and CA2, CA and CB, and this is your second reactor, CA and CB. Any doubts on this? If not, let me move to the next part of the question. That is a time requirement for reaching the steady state. So again, here you know that, okay, time requirement for reaching the steady state means the one thing is you need to be able to visually identify it because you don't want to make mistakes. Okay, visually, how do you identify it? Visually, you see that the CA and CB goes higher and higher, and finally it reaches an horizontal behavior. It forms a horizontal line like this. That is, goes on increasing like this, and finally it will go like this. Okay, this is called a steady state. Once it goes like this, okay, but that is even the time changes, you have the concentration to remain the same. Okay, so this is called the steady state concentration. Once this behavior is reached, you can say that it's reaching steady state. So it's very important that though you might write a request, write a code to identify the time, it is better you plot also, so that you can visually confirm that okay, your code is not giving any like you any wrong values. It is actually physically meaningful. Okay, the system has reached steady state. So it's very important that you code it also. So it's very important that you plot also along with your code. So let me just show you. Let me just close this figures. Am I sharing Matlab? Okay. So the everything remains the same here. You have your clear all and all these things. Here instead of running for 0 to 10 minutes, I'm running for 0 to 60 minutes. Okay. So what I'm doing is the CSTR, this remains the same. I'm running this calling the CSTR and I'm running for 0 to 60 minutes, not 0 to 10 minutes. Why? Because in earlier I had observed that even within 10 minutes, both the concentration is in the reactor one and the reactor two, it has not reached the steady state. Okay. Now we have the initial values all given to be 0, 0, 0. Now what I do is I want to see when it is attaining the steady state. How do you know that if it is attaining the steady state? What I can do is I can calculate the gradient of concentrations. That is how much the concentration is changing. The thing is, let's go back. See, steady state means change with respect to time will be zero. That is, this will be go to zero, this gradient will go to zero, this gradient will go to zero. So your ODE will give you time values and CA1 value, CB1 value, CA2 value, CB2 values. If you're able to numerically calculate the gradient, okay, and if you're able to check if the gradient is zero at some point, then you can say that, okay, the steady state has attained, that is this gradient is zero. So the ODE gives you CA1 and T, CB1 and T, CA2 and T. From that, you have to manually calculate what the gradient is and identify the point where the gradient is zero. When the gradient of all the four systems has attained zero together, okay? And then the minimum time at which all the four concentration has attained steady state, that is all the four equations has come to zero, that is called as the time required for the system to attain steady state. Okay, the minimum time. So this is the logic behind it. Now going to the MATLAB code, just a second. Okay, so here we have the ODE solver. The ODE will give you T and C solve. Again, one thing is here, the time and as I said earlier, the time will not be uniformly distributed, which we already saw in T solve, right? In T solve, the time will not be uniformly distributed. Now we will have to make this time and concentration at equal intervals. How do you do that? So for that, what I do is from 0 to 60, I'm taking a time interval of 1. So this is uniformly divided time interval. And then I try to interpret what is the concentration at this time intervals. For that, we have already done this. We've already seen this function interrupt one. Okay, this function in MATLAB which you've already seen. What does it do? It does interpolation. That is, if you keep T sol and C sol, and you're telling that I need to find the concentration at the new time interval, that is T fine, using spline interpolation. This is a method. You can go use this help function for interrupt one. It will identify the several options that is available to you. Here I'm using a spline interpolation. Now what I get is for this equal intervals of time, I'll get the what is the concentration. Remember in this concentration, there will be four concentration. The first column will correspond to CA1, second column will correspond to CB1, third column for CA2, and fourth column to CB2. Okay, this difference will be there. So once I have the uniform concentration, then I use calculate the gradient. So for that, I'll be using the MATLAB inbuilt function gradient. I'll just show you how the gradient works. Help gradient. Okay. If you're giving a gradient function, returns a numerical gradient of the matrix F. So if you give something here, it gives you numerical gradient. dfx corresponds to df by dx. The difference is in the x direction. df dy corresponds to the difference in the y direction. Okay. Then other point is the spacing between the points in each direction is assumed to be 1. This is very, very important. We are assuming that the spacing between the entries is 1. So here that is the spacing between the time has to be 1. So that's why we use this t fine with an interval of 1 here. Okay, you see that interval of 1. So this is why, because this gradient function works when your entries are of the interval 1, unit interval. Now what I do is I try to calculate the gradient. This is my gradient of the C fine. Okay, let me just run till here. Run section. I'll show you T fine. This T fine you have from 0 to 60 you have it. And C fine is this. See, everywhere starting from 0, 0 only. But you have here, this is your CA1, this is your CB1, CA2, and CB2. Okay, C fine will have all the 4 quantities, out of which I need to calculate gradient separately. So basically, I'll be choosing gradient. The input will be the first CA1, that is all rows first column. And this is gradient input will be CB1, that is all rows second column. And the third will be gradient of CA2, that is all columns, all rows third column. And next will be CB2, that is all rows fourth column. Okay, so this is the gradient that has been there. Now I'm also, so this T fine, you saw that it was a row vector. Now I'm trying to make it as a column vector. So that is why I'm transposing this vector. Then I am using a concatenate function. So if I'll do this help cat, hmm, help cat means you need to give the dimensions a comma b. Okay, if this dimension is 2, it means that you are arranging it is like column wise. Okay, this is the same as a comma b. And if you're writing cat 1 comma a comma b, that is this corresponds to a semicolon b. Okay, I'm concatenating all these arrays. So I've concatenated these arrays here. So if I just run this portion, I'll show you. Evaluate section. Okay, grad RR looks like this. Okay, this corresponds to the time. This is CA1, this is CA2. This is, sorry, this is the gradient, not the CA1. This is the gradient of CA1, gradient of CB1, gradient of CA2, and gradient of CB2. Okay, so that is concatenated into a single matrix like this, which is having 4 columns. Now what I do is I check if any of the gradient is less than the grade tolerance. What I require is I want the gradients to go less than 0. Sorry, equal to 0. So I'm giving a tolerance, a very low tolerance of 0.001. You can give a much more tighter tolerance also. It's completely fine. Now I check if any of these gradient values are less than grade tolerance. Now what will this give? It will actually give you a matrix of 0 assignment. That is, if any of the entries is greater than grade tolerance, it will give you 0. That is, the condition is not satisfied. That is binary 0 and 1. But in case this condition is 2, then it will give you 1. So this is a logical array. See, initially you know that system has an attained steady state. So it's all 0, 0, 0, 0, 0, 0. Finally, you see that at some point, so maybe at this point, see at this point, you'll see that all the concentration, that is CA1, CB1, CB2, CA2, and CB2, all this has gone below the tolerance level. So this is where the system attains steady state. So what I do is, I do concatenating it column wise, transpose of T fine, and then I sum it, sum A comma 2. That is, I sum the column wise, I sum it. Okay, if I use help sum, you need to understand what does each dimension mean. Okay, one corresponds to row, second corresponds to column. So see, x comma dm means it sums along the dimension div. So it sums along the columns. Now what happens is, you are taking if the sum is equal to 4. Why equal to 4? Means all the 4 concentration has to be less than tolerance. So there will be 4 ones there. Therefore, the sum is equal to 4. So we are telling that the sum is equal to 4. And then we are trying to identify. So I'll say you, if A we have already said. Now I'm calculating this part of the equation. Just a second, I'll just evaluate this. Not able to select. Just a second. Okay, now I'll show you what sum does. See, this is time, and then you have the sum. So earlier you have 0, 0, 0, 0, 0, 3, 3, 3, 3, 3, and finally it is 4. Now I'm telling I'm extracting the portions where the sum is equal to 4. Now I'll evaluate the selection. So that's again a logical thing. You have 0, 0, 0, 0, 0. Sorry. And finally, here only I get ones. Okay, that is whether if it is not equal to 4, the binary operator, it will be 0. If it is equal to 4, then then what you will have the binary 1 here. So this is also a logical array. Now what I do is I understand what is the minimum of this B. So here, I'll put this portion just a second. Sum of B is this. Okay, that is whatever the answer is. So that is the it will give you the indexes where B is giving 1, 1, 1. That is 55, 56, 57, 58, 59 till 61. Okay, that's what this is giving. Out of that, I take the minimum. That is 54. That is when time is equal to the 54. 54. Here we have divided 0 to 60 minutes by an interval of 1. So we have 54th minute. You have the all your concentrations going below the tolerance. So that is the time when your system reaches a steady state. Okay, the system will reach steady state at that point. TSS. So let me just clear all this and run this for you once again. You'll understand that the system has reached steady state at the 54th minute. Okay, is this clear? Are you clear how each part of the question has been done? Any doubts in any of the lines? Okay. Now coming to the next part of the question. We have studied the evolution. We also understood the time requirement for reaching the steady state. Next question is identify the steady state concentration. This has not been given to you in the question. This is just an extension. Okay. If you understand what's the steady state time, we need to understand what's the steady state concentration. There are several ways to do it. Since you know the time, you can give the time into the ODE equation and you can identify what's the steady state concentration. That can be done. Another way to do is you know that these four equations has to go to zero, right? So this four equations are equating it to zero. Now what happens? Ignore this portion because this is nothing but zeros. Now you have a set of algebraic equation, a system of linear algebraic equation. You need to know how to solve this linear set of algebraic equation. This you've already done in the previous classes. So we'll be trying to do the same thing. Just give me a second. I'll show you the code. See, you have the CSTR-SS. I'll just show you CSTR-SS what is happening. Okay, I think I don't have that thing right with me. Oh yeah, sorry, it has been written here. Okay, the function CSTR-SS, what you do is you write the whole four equations in a column vector. Okay, and you use fsolve to solve it. This example with fsolve we have done in the previous classes, so I'm not going through it again. So here you have your C is a vector which has your first element is CA1, second element is CB1, third element is CA2, and the fourth element is CB2. These are the constants that has been given to the question. What you do is you may write the first equation, first algebraic equation, second algebraic equation, and so on. There has to be a column vector. That is four rows and a single column. You have to write all the four equations. And then what you do, you give that equations into fsolve with your initial value for CA1, CB1, CA2, CB2. Okay, and then you get the equation, the linear set of algebraic equation is solved by MATLAB, and you get the concentration corresponding to that. Out of which again you have to extract. This will have four values. The first value corresponds to CA1, second value corresponds to CB1, third value corresponds to CA2, and the fourth value corresponds to CB2. Okay, and I'm also printing it here. Right now I'll just run this equation. Sorry, run this problem. See, your fsolve has been completed. Equation is solved. And finally, the steady state concentrations all given in moles per liter is Ca is 12.5 moles per liter, Cb is 7.5 moles per liter, Ca is 7.8125 moles per liter, and Cb in reactor 2 is 12.1875 moles per liter. Okay, so attaining the steady state concentration has not been given to you in the question, but it's just a small addition. How do you do it? You have to just equate the equations to zero. Then you will get a set of linear algebraic equations. If you have a system of non-linear algebraic equations also, you know how to solve it using fsolve. Okay. So I'm not repeating that again. You can get non-linear algebraic equations. So that system also, how to solve it, we have done it in the previous classes. I hope it is clear. Any doubts? Okay. If no doubts, let us proceed again. Study the effect of space, time, and rate constant on time requirement of to reach steady state. Okay, this is a very important part. That is, we have so far we only did our studies for a constant time space time and a constant rate constant. Okay, also tau in your k was fixed. Now what do you do is you vary for different tau's. You understand how the system behaves. You also vary to different k's and you study how the system behaves. So this also a small part of this core thing we have already done it in our previous classes. What do? You create a for loop. In the for loop, you will have different space times that is given. For one space time, you do the calculation, you plot it, and for the second space time, you again plot it. You do that accordingly. Okay. So when you are studying space time, you keep the rate constant as a constant value. Again, if you're studying the effect of rate constant, you fix a space-time to be a particular value and you keep changing the rate constant to various values. So here what we're trying to do is, here we are varying k from 0.1 to 0.5 to 1 and your space-time is being varied from 1, 2 to 5. Okay, and this you can do it for reactor 1. So here I've only shown the results for reactor 1, but similar thing you will get for reactor 2 also. So basically you will have these are 6 plots. Again, you will get another 6 plots from your question. So let me just show you the code for that. Sorry. See, here what I do is every part of the question remains the same. Just that I have a vector of two values. Here I'm doing it for the different space time I have fixed. Okay. So now what I do is I run for space time equal to 1, tau equal to 1, tau equal to 2, and tau equal to 5. Now what I do is I start a for loop. And the for loop has to go from tau equal to 1, tau equal to 2, and tau equal to 5. So first I have the I ranging from 1 to length of tau is. That is, it will go to the 3 times it will go through the loop. In the first loop, I'm taking the first tau. That is tau 1 will come. So that is a 1 value here. Then I'm using an ODE solver. Okay, and this is a function that I'm using. I'll come to this function later, but this has three inputs. T is there, C is there, and tau value is also there. That is also an input given by me. Okay, it is not written in the code explicitly. This has to be given as an input. I'm running it for 0 to 60 minutes, and these are the initial values. Now looking at CSTR tau, what happens? Everything remains the same. K I'm fixing it to be 0.12. CA0, this I'm fixing it to be 20. Was it 20 earlier also? Just a second, let me just look. Yeah, it was 20 earlier also. Now what I do is, I write all the equations. Okay, these equations are right, similar to what I wrote earlier. Same equations. Okay, four equations, I write it as these coupled equations. Because of that, I write it as a single column, multiple rows. And here, tau is an input. Remember that tau is an input that is given by the user. Now what I do is I run this CSTR equation. I get CSOL. CSOL will have four elements. The first element will be the all rows. First column will be CA1. All rows second column will be CB1. Okay. All rows third column will be CA2 and all rows fourth column will be CB2. I extract elements like this. Okay. Now one additional thing also I'm doing, and other than studying how the system behaves, I'm also trying to study what is the steady state, the time at which time at which the system reaches steady state. This is for this particular tau and particular k. This might be an extra thing. It's not given to you in the recorded lectures. This I've just added so that you know how to club the parts that you've already coded. Now, how to do the steady state time? So for that, I've written a separate code, steady state time. Okay. This remains the same. The logic remains the same as earlier, the B part of the question. So here what you do is I'm doing it till 60 minutes and the tolerance is below 0.01. Okay. I already have so what happens is the steady state time, whatever I wrote here, will take two inputs, T-solve and C-solve. Okay, for this particular case, okay, so this is inside the for loop. Remember that. Inside the for loop, I get the T-solve and C-solve from the ODE. That is used as an input for the study time. Then what I do is, for this T-solve and C-solve, I have to divide into equal intervals. Only then I can use the gradient function, right? So I divide into equal intervals using spline interpolation. After that, I calculate the gradients. And then how do I calculate steady state? That this part I have explained to you step by step. Okay, I hope you guys understood that. Then I print it. The system will reach steady state at the so and so time. Okay, so this I have just added this part of the code into inside the loop. So that for each condition you'll get the steady state time. Now again it will do for tau equal to 1. Again it will go back to the loop for tau equal to 2. Again it will run. Okay. Remember in all these cases, if you see k is kept as a constant. Okay. Now I'll just run this part for you. I don't know whether you can see this. There are multiple plots here. Okay, this plots might vary based on the k value that I give. Here I've given k equal to 0.12. You can give a different k value also. That is also completely fine. You will get the system behavior like this. Okay, I'm not showing you everything. I'll just close all this. Have the result that is there given in the PPT. Maybe that is easier for you to see. Okay. Now what happens is the result will go. See, this is what happens. This is only for reactor 1. Reactor 2 also you can obtain similar graphs. So for reactor 1, when k equal to 0.1, what happens is you'll see that your A has been going up and your B initially it is very slow, but as then it slowly progresses. Okay, A converting it to B. This is when K equal to 0.1 per minute. Now when I'm sorry, this is tau equal to 1. This is what I've tried to study. Tau equal to 1. That is space time equal to 1 minute. Now I'm increasing the space time to 2 minutes. That is now my elements A and B is there in the reactor for a longer duration. What happens when there is a longer duration? When there's a longer duration, your A gets converted into B. The conversion happens, more conversion happens. Okay. So your A value and your B value, the equilibrium, what happens? There will be more B value compared to what we got earlier. So earlier in the equilibrium state, your B value was close to 7 mole per liter or something. Now, since there is more space time, more reaction would have happened. Now your equilibrium B value will be higher. So here you can see the equilibrium B value is close to 10. Okay. And you can see the equilibrium A value. Earlier it was some 14 or something. Now there is more conversion happening. So the A value has decreased. Now your equilibrium A value is close to again 10 or something. Okay. This is what happens when you give more space time, more reaction happens. Now the same thing you can observe when you're increasing the space time even further. That is K equal to 5 minutes. Now what happens? Now more A would have converted into B. Now if you look at the equilibrium concentration, your A concentration is 5. It has even dropped from this value. Okay, it was earlier 10, that is now dropped to even 5. The equilibrium has reached to 5. And your B equilibrium has raised. Earlier it was close to 5. Now it has even risen and now it is close to some 14 or something. Okay, so now because more space time, you have given more time for the reaction. So more B is found. More A it converts to B and you're giving enough time for that. So this is how when you're increasing the space time, this is what happens. Okay, k equal to 1, tau equal to 1, tau equal to 2, and tau equal to 5 minutes. Any doubts in this behavior? Okay. Now we can do the similar thing for studying for different values of k. So here we are intending to study k equal to 0.1 per minute, k equal to 0.5 per minute, and k equal to 1 per minute. Okay. So let me try to do that. So the same thing you can extend here. See, everything remains the same, just that I have like a k that is ranging from 0.1, 0.5, and 1. Okay. Here I have a loop that takes each k values. So first it takes k equal to 0.1. I have an ODE solver. In that takes ODE solver inputs are what? T, C, and this time k is the input. Okay, because tau is fixed. Again, I'm running for 0 to 60 minutes and all the initial values are 0. I will show you this code. See, tau is I have fixed it to be 2. It could be any value. Right now I have fixed the value to be 2. Okay, and the initial values, these equations are similar to what we wrote earlier. Any doubts in this? Okay. And one more thing, when I ran this equation, you can see for tau equal to 1, system reaches steady state at 12 minutes. For tau equal to 2, the system reaches time steady state at 22 minutes. Okay, because more time you're giving, so more reaction is happening. So it will be steady state, like it will take a little bit more time for reaching steady state. At tau equal to 5, the system will reach steady state at 54th minute. So this also, please note, this has not been given in your recording. So please note this behavior also, how the steady state time is changing when you are varying your tau values. Because you increase your tau values, your steady state time is also increased. It's directly proportional. Now coming into the K, varying K, I hope that this part is clear to you. Here K is the input, tau is fixed. K is defined by, it's given as an input to this code. Now again going back, you again plot CA1, this is CB1, this is CA2, this is CB2. And again, I'm using the same steady state, this function I'm using again. It will take T-solve and C-solve. And I just divide it into equal time intervals. I calculate the gradient and I find the time where the gradient goes to 0. So that is my steady state time. I hope this is clear. Let me just run this part again. Sorry, this one. See? For k equal to 0.1, steady state reaches at 23, k equal to 0.5, again 23, and k equal to 1, it is 24. So now you can see the variation is little, but still you can see as the k varies again, your time for the system for reaching the steady state, that also increases. Okay, it is also directly proportional to value of k. And how the system behaves again, there is like, I can show you the plots here. There are several plots, but going to the PPT, I'll just show you each and every plot together. Just a second. Yeah. So this is for reactor 1. You will see initially when K is equal to 0.1, you have like larger equilibrium concentration of A and lower equilibrium concentration of B. Now when you're increasing K value means there is more, it is more reactive. A is more reactive, which means there will be more B formed. Again, you can see your B has shooted up. Earlier, your B equilibrium concentration was close to 5. No more B has been formed. Now your equilibrium concentration of B is like close to 14 or something, and your A has reduced because faster reaction. So more A forms to B. Okay, more A converts to B. So your A equilibrium concentration is 5. Again, when you're increasing K even further, that is more reaction is happening. More B is formed, so there is lesser A. So more B is formed. So the steady state, you can see it in this graph. Maybe you'll have to run it for more time interval. Again, your A equilibrium concentration has been dropped from 5 to even lower, maybe 2.5 or something. Okay, so here you can see both K and tau. If you're increasing space time means there is more reaction that's happening. If you're increasing the reaction rate constant also, more reaction is happening. The same behavior you'll observe in the reactor 2 also. You can do, you'll get plots also, you can observe that. Any doubts? Is everything clear? I hope you understood how to calculate the steady state time also. Steady state time also we observed that if you're increasing K, also your steady state time increases. If you're increasing tau, also your steady state time increases. Okay. Any more doubts in this area? In any of the question parts? Any doubts anywhere? Okay, now let's move forward to the questions. I'll give you like a few problems. We have around like 16 to 70 problems. It is similar to your assignment questions. I'll give you 2-3 minutes to answer. If you have got the answers, you can just put it in the chat box. There'll be also questions that will be based on Matlab, where you'll have to write codes and solve in Matlab. So please keep your Matlab ready. I'll give you time for that also. Write your codes and let me know the answers. Right now, I hope that you guys are okay with solving ODE equation, coupled ODE equations. We have solved few examples in your previous week also. So if you want to know more about coupled ODEs, you can visit the previous lecture also, okay, where we have done few more examples. Here we'll solve more examples and more problems that is associated with this CSTRL series. So for this is the first question. I'll give you like 2 minutes. Please let me know the answer in the chat box and then we'll discuss the answers. Any answers for this question? As per the analysis conducted in the lectures, which of the following is assumed to remain unchanged with respect time in an unsteady state CSTR? Okay, so in a steady state, you know that okay, in a steady state when your system has attained, you know that there is no change with respect to time, right? Even the concentration temperature, nothing changes with respect to time. But here, when the system is in unsteady state, what happens? Concentration changes because your system is evolving, your reaction starts to happen, so there is change in concentration. If you are dealing with an adiabatic system, then you have like if you're not so if there is a heat transfer that is happening, just like we saw in the earlier lectures, then there is a temperature change also that is happening. The only thing that doesn't change is the density. Okay. The flow rate also can be changed during unsteady state, and the density is what that doesn't changes in an unsteady state of CSTR. Any doubts? Okay. Now moving on to the next question. I'll give you 2-3 minutes. Please put the answer in the chat box. You can just write the option A, B, C, or D. And then we So what was the question we had? Which of the following combinations is correct for unsteady state isothermal operation? That is constant temperature operation. So here we have the concentration of a species as independent variables and time as a dependent variable. Okay, concentration is an independent variable, time is an dependent variable. Is this right? No. The second option is concentration of species as dependent variables and time as independent variable. Remember, this is unsteady state. Okay, so in unsteady state, we have things varying with respect to time. So here we have concentration changing with respect to time. Okay, so option B is correct, but anyway, we'll go through option C and D. Concentration of species as independent variables and temperature as a dependent variable. Is temperature dependent? No. And again, the D option is concentration of species as dependent variable and time as independent variable. Is option B and D the same thing? I think I've made a mistake here. Yeah, actually, sorry, this was temperature. I read it wrong. Okay, we are start talking about unsteady state. Here, isothermal means temperature is not at all changing. So it's not even a variable there, it's a constant thing. And unsteady state means everything is changing with respect to time. So concentration as a interdependent variable and time is an independent variable. I read this wrong. Okay, time temperature is not the independent variable. Everything is changing with respect to time. So option D is correct. So concentration of species is dependent variable and time is independent variable. Okay, is it confusing or is it clear for everyone? Okay, now moving on to the next question. Which of the following expressions is correct for unsteady state mass balance equation of two CSTRs in series for a first order reaction? A given B. Okay, please try to solve it and then we'll discuss the answer. You can take a pen and paper and try to solve this. We have already given some equations earlier, so please try to recollect that and then we'll try to solve it. So the answer is second one, DC. So we can just compare with the equations. So right now, let me just compare this one. A2, we had already written equations. Yeah. So A2 equation is by 1 by 2 CA1 minus CA2 minus KCA2. Okay, I hope you remember these equations. Let me just show you. Okay, so he can compare 1 by 2 CA1 minus CA2 minus KCA2. So this is your CA1 equation. CB equation is false because here it has to be plus KCA2. And again here, this has to be minus has to come here. So there is a sign problem here. And then again in the B1, you have like it has to be plus KCA1 because after the reaction, actually the B concentration is increasing. So here there has to be a plus. Now coming into the A1's concentration, also you have here CA. Okay, in A1 it has to be CA0 minus CA1. So here CA2 is not there, so there is a mistake in that. So the only answer is option B. That is dCA2 by dt is equal to 1 by 2 CA1 minus CA2 minus KCA2. Any doubts in this? So if not, let us move to the next question. So this for this, you'll have to use MATLAB. So I'll just read the question for you and I'll try to give you small hints. We have a system where there is a series reaction, A giving B, B giving C. And there are three equations governing the concentration of Ca, Cb, and Cc. The equations are given to you. Initial condition is when your system begins, your A0 is 100. Rest of the concentrations are 0, 0. Analyze the concentration of Ca, Cb, and Cc in a batch reactor for the following cases. So remember, you have the multiple cases that is given here, so it is better you use a for loop. Okay, and try to plot the Ca behavior, Cb behavior, and Cc behavior. So please try to code this in MATLAB, and I'll come with the answer like in 3 4 minutes. Okay. So let's look at the MATLAB equation. So MATLAB, the code, just a second. So here, let me first give all the initial concentrations that is given to me. CA0 is 100, CB0 is 0, CC0 is 0. So my initial vector is all, I have just clubbed it into it. You can directly write 100, 0, 0. That's completely fine. Now T-span, I am just writing for 0 to 5 minutes. Now what I do is instead of writing two for loops, I've just divided this into cases. So this case will look like this. Let me just let me just show this to you without a semicolon so that you get it printed. The case looks like this. Okay. This is first case where k1 equal to 2, k2 equal to 1. This is second case where k1 equal to 1, k2 equal to 2. And this is the case, third case where k1 equal to 1, k2 equal to 1. Just like what is given to you in the question. Okay, I'm writing a vector like this. Now what I do is I run a for loop so that it goes to each and every cases. So for the first one, I take cases. It goes, how many cases are there? There are three cases, right? So it has to loop three times. So I'm giving the one column size cases comma one. So this takes a number of rows. So that is equal to three. So your loop runs for three times. Now what is your K1? K1 is nothing but whatever this gives you the row number. And the first column gives you K1. Second column gives you K2, right? So K1 is your cases, first column, first row. K2 is your first column, sorry, first row, second column. So you have extracted your K1 and K1, K1 and K2. Now we need to write the reactions. So in the reactions, what are the inputs? TS is an input, C concentration is an input. You have K1 and K2 as an input. I'll just show you that code also. So this is the reactions code. This is not necessary. Basically, here you'll have the T. Okay. So T is there, C is there, K1, K2 is there. Out of C, you know there are C is a vector, right? So the first entry will be for A, second entry is for B, and the third entry is for C. So write all the three equations separately, and you can club it to form a column vector. You can do that, or else you can write dc by dt, the first column, that is semicolon comma 1 is equal to the first equation, like we were doing earlier. That can be also done. Or else write three equations separately and club them together here using semicolons to form a single column vector. Is this clear? Any doubts? Okay. Now going to the first part, I have for a particular case, I run the ODE. Then what I do is I'm trying to plot. So in the first plot, I'm plotting the first A concentration. The second column will give me the B concentration, and the third column will give me the C concentration. Okay. So this is, I am trying to plot it as subplots. That is, it will have 3, comma 1. It's a subplot. I'll just show you the help subplot if you have not seen subplot before. See? When you're writing subplot M n P, it means it divides the entire figure into M by N grids. That is M rows and N columns. Okay, so here I'll get 3 rows and 1 column. So 3 rows means what? 3 rows. First is for the case 1, second row is for the case 2, and the third row is for case 3. And this I will correspond to the which figure I'm writing now. So here I will be 1, right? So initially here I will take 1, then it will take 2, and then it will take 3. So first one, I'll get the first plot for the first case and the second subplot. When I equal to 2, it will be the second subplot. When I equal to 3, it will be the third subplot. All will be arranged as a single column. Okay, I'll run this code and then you will understand. I'm adding all the X labels, Y labels accordingly. Is this code clear? Now again, when the loop goes to I equal to 2, it will take the case number 2. And it will extract K1 accordingly, K2 accordingly. Again, you will run the ODEs and it will get the plots. I'll just show you the plot also so that you can compare with your results. This is a behavior that you get. Okay. So this is for K1 equal to 2, K2 equal to 1. First case, you will see how your A, B, C, everything is changing. Okay. Because I can just give you a quick comparison like what physically it means. When your K1 is equal to 2, this means that your A is reacting faster. So what happens? Your A will drop very fast compared to the rest of the two. Here K equal to 1, which means A is reacting slowly. So the drop is not very rapid. Here, when the K is reacting fastly, the drop of A is very fast. And the same, because of that, you can see the rise of B is also faster, higher compared to the previous, compared to the lower graphs. When K2 equal to 1 means what happens? Now let's compare K2 1. K2 means B reacting to form C. When K2 is, this K2 is 1, here K2 is 2, which means this reaction B converts faster to C. Because of that, you can see that the drop of B is higher compared to here, and you will see the C is also forming rapidly here compared to the previous case. Okay, here C forms 50 in 1. Here C forms like, yeah, here you can see how the behavior of C and A changes. So this is how you can try to make a physical interpretation of it, varying by the K1 and K2 values. You will be getting the three rows. This is corresponding to the first case, this is corresponding to the second case, and this is corresponding to the third case. Is it clear? Any doubts? This reaction, this behavior we have seen in the previous class. Your A continuously keep dropping because A is converting to B and B is converting to C. And since your C is your final product, it will continuously keep on increasing until it reaches steady state. But B, what happens? Initially, B is formed. And as soon as B is formed, it is converted into C, right? So because of that, initially there will be an increase in B concentration. It will reach a maximum and then the B concentration will decrease because the B is converting into C concentration. So this behavior will be like this. It will increase, then there will be a small peak and then it will keep on decreasing. That behavior you can see in all the three cases for B. Is this clear? Okay, now let me move on to the next part. The same question has a B portion. So let me do that also. Now analyze the evolution of this concentration A, B, C for K1 is specified, K2 is specified. Right now the initial concentrations are varied. Earlier the initial concentrations were fixed. Now what I'm doing is K1 and K2 is fixed, but the initial concentrations I'm varying. So there are three cases of initial concentrations. So just try to modify this already written problem. I'll give you just 2-3 minutes and then we will discuss the answer. Anybody with answers? So the same problem we'll try to extend a little bit. Earlier, what we have done is we created a vector for different cases, right? Right now, we'll create for different cases. That is, for each case, we'll have a different set of concentrations. So let me just show you that. So everything remains the same. Your K1 is fixed, K2 is fixed. Now we'll write the cases. The first case, this is for CA1, CA2, CA0, CB0, CA0. This is the second case, CA0, CB0, CC0. And this is third case, CA0, CB0, CC0. Now again, just like we did looped over different cases of K, here we'll loop over different cases of Cs. So here what happens is initial cases, one means number of rows. How many rows are there? There are three rows corresponding to three cases. So for the first case, we'll take, and then what happens is we take C0 is nothing but the whole vector, basically CS0, CB0, CC0. That goes here. See, C0 is initial case. You extract that particular row, and that goes as an input here for the ODE solver, right? And again, if the ODE solver solves it, the reactions I can just show you. Do I have that with me? Let me just run this code once. Yeah, CC0 is there. Everything remains the same. The code also remains the same. Reactions functions can be the same, okay? Because T, C, K1, and K2, these are the inputs. Here, just K1, K2 is constant. That is the only difference, but that doesn't make a difference in this reaction code. Only here, in the ODE initial case, this is where the main difference comes. And then I plot three subplots here into a single plot. We have already seen that. Let me just run this. So this is the plot you will be getting. On both CA0, CB0, CA, the initial is 10. What happens? A drops. Your B also drops, but your C is the final product, which keeps on increasing. Okay, this behavior we have already seen earlier. This is only the slight difference one. Your A drops to form B. Again, B drops again. Finally, C is formed. So this is what the difference of initial concentrations makes in the evolution of a concentration. I hope you can compare your answers right now. Shall we move on to the next question? So moving on to the next question. So it's a correct statement. There could be multiple right statements. So please read it carefully and let me know the answer in the chat box. Any answers for this question? So choose a correct statement if increasing K if the reaction is tending to A giving B. So increasing K means there is more reaction that is happening. So that you have to first recognize that. Now concentration of A will be higher and B quickly reaches a steady state. Okay, will that happen? Uh, A quick reaches a steady state and concentration of B will be higher. Okay, probably that is going to happen. Anyway, because the rate of reaction is higher, so it is more likely that there will be a higher concentration of B than A. Now, steady state concentration of A is the highest for the highest value of K. Will that happen? Steady state concentration of B will be the least for the highest value of K. So basically, the A B will happen because there is more reaction that is happening. So there will be the higher concentration, higher steady state concentration of B than A. So that is what is going to happen. And since K is faster, there will be a faster reaction. There will be a quick attainment of steady state. Now, I hope this answer is clear. Now, going on to the next question. This you have to use MATLAB. And please read this question. Okay, I'll just read it for you, then I'll give you time for coding. A simplified model for the growth of a flame can be expressed by this ODE, dz by dt. It's a single ODE. Z is the height of the flame. After ignition, the flame grows very fast to reach a critical size. The initial condition is Z of 0. The initial height of the flame is 0.01 units. Determine the time requirement for reaching the maximum flame height. So, which means the flame height is going to increase from 0.01. It will reach a maximum and then it's going to drop. So now what we need to identify is the time requirement for reaching this maximum flame height if the system is studied up to t equal to 150 seconds. Okay. Now we have to use ODE 15 years. So I'll give you two tips. First, use ODE 15 years. It's a single ODE, so it'll be much easier to solve. Now what you have to do is try plotting it. Okay. Try to plot it so that you can physically observe what is the highest point, and also try to write the 3 or 4 lines of code so that you can identify where this maximum is. And one more tip I can give you is at the maximum, this dz by dt, that is, it will be a horizontal point. The dz by dt will reach 0. So if you are able to calculate the gradient and if you are able to find the point where the gradient is 0, okay, that is going to be the maximum point. Okay, that is a hint that I'm giving you. Now take like some time and then try to solve this, and then I'll discuss the answer. Any answers for this? I'll just quickly share MATLAB. And let me just close all these files first. So the first solving the ODE portion. So first solving the ODE portion is pretty easy. So we have the equation. T-span I'm doing from 0 to 150 seconds. And the is the initial concentration, initial height is 0.01. And then I'm using an ODE 15A solver. This is the function I'm directly writing here because it's a single simple equation. Z square minus Z cube for the T-span of 0 to 150 seconds. But the initial height of the flame is 0.01. I'm trying to plot this. So first I'll try to plot this here. Let me just run this section. So this you can observe here. Sorry, Matlab is, just give me a second. Okay, this is what you observe in MATLAB. You'll be the flame height is increasing, it will reach a maximum, and then it remains in the maximum. We need to identify the exact time at which this maximum is reached. So this is how the system behaves. Now let us try to identify, either you can directly take it from the graph, but that could be a little bit tricky, or then we'll identify how to use the MATLAB coding for getting the maximum flame height. So for that, what you do is you calculate the differentiation. Either you can calculate the gradient, that is completely fine. That is by taking t and z, you know that it will be a variable time step. So you can use interpolation, create equal time intervals and equal z. And then you can calculate the gradient, and then you can find the point where the gradient is getting to be 0. Like we did in the previous examples, that can be done. Or else what you can use is there is an inbuilt MATLAB command which is called as DIF, that is differentiation. So you can do differentiation of dz by dt. You can directly find it using this formula. Okay, you can just go help diff. You'll be getting this. Okay, differentiation of this vector. Basically, you'll be getting uh, the uh, the difference between the two consecutive readings. So dz by dt, you'll be getting a vector of it. Now I'm taking a threshold that it has to be close to 0. So here I'm taking a threshold of 1 e raised to minus 4. Now what I do is I check if any of this value is below the threshold. Okay. So if I get a value below the threshold, then what I do is if it is empty, then I write, okay, the maximum flame height is approximately, sorry, if the steady state is not, it's not empty. Okay. It's empty, not, it's this simple means not. So if this is not empty, then what I do is I write the maximum steady state time is the given by this one steady time, or else I say that, okay, the flame has not reached the 150 seconds. So let me just run this code for you. Threshold is there. I have ran this already. Steady IDX is this 42. Okay, exactly the point where the the dz by dt goes to 0, and it has to be the first value. Okay, this is how you can use the inbuilt MATLAB command find. See? Find means you can find a particular value. So he can find a value where the absolute value of dz by dt goes to 0, goes less than the threshold. And I only need the first place. First means it's the same as I equal to xk, which means that, okay, I'm looking at the first index at which it goes below the threshold. So I get the steady state time. So if the steady state time is found, then I print it like this. I can run the code again for you. Just a second, I'll run the code again. Now we'll get, if the code is running properly, then you get the maximum steady state time is attained as 11246. In the plot also, we'll just confirm it. 11246 means it's somewhere here. Okay. Yeah. From the graph, you will I get that, okay, it's somewhere close to 110. Okay, so the actual answer is 112.46. That is the time when the steady state height of the flame is attained. I hope you have understood this. Now we'll move on to the next question. So as per the analysis done in the lectures, to get the highest concentration in B in reactor 2, what should be the right answer? So if you have the answer, you can just put it in the chat box and I'll discuss it in like a minute. Just give a thought to it and then I'll discuss the answer. I hope you know this. We've already said that if we increase the space time, there will be more concentration of B. That is, there is more reaction that is happening. A giving B happens. There is more time for that. So more, there will be more concentration of B. Similarly, if the rate constant is high also, there will be a higher reaction of A giving B. Therefore, there will be a more concentration of B. So in our case, for getting a highest concentration of B, we should have both the space time and rate constants to be higher. Okay, because both are directly proportional to the concentration of your B. Is this clear? This is what we have understood from the graphs. Like we have the third part of the question where we identified the relationship of space, time, and the reaction constant K to the concentration of A and B's. And we observed that when both space time is higher and reaction rate constant is higher, there will be more generation of B. Now, again, this is a question which you have to do it in MATLAB. You have two equations, two coupled equations. Y1 and Y2 is a variable. You are given the initial guesses also. What you need to find out is a Y2's concentration at T is equal to 10. And there have been options also given to you. I'll give you like 2-3 minutes and then we'll discuss the answer. If you have MATLAB, please open MATLAB and try to write the few lines of code. And then we'll discuss the answer. So we'll let us quickly discuss the answer. I'll just share MATLAB. So T span is 0 to 10 seconds or minutes. What was given to you in the question? T equal to 10. That's it. So now T equal to 10, 0 to 10. Your initial Y1 is 0.95, Y2 is equal to 0. You run ODE 45. I've written a code for ODE systems, which will save all the equations for you. So ODE systems is here. It will take you T and Y. Your first Y is Y1, second Y is Y2. I've given the two equations here separately, and then I club it to form a single column vector. Or else you can do it here also, just like we used to do before. This is also fine. After the ODE systems equations are given, I run the ODE. Now remember that I run it for 0 to 10. Okay, and the question is to find the value of Y2 exactly at the 10th point. That is 10 T equal to 10. That is the last point. So what will be my last value? My last value is, if I run this clear ELC, I'm just running it. So this is how the graphs looks like. Okay, this is how the graph look like. You can see the Y values dropping from 0.95 to somewhere close to 0.18 or something. And then, so the Y value is, sorry, it is close to, oh, it is less than 0 actually. It is 0.062. And your y value, y2 value is going from 0, it increases finally and it again drops. Okay. So now what happens is this is the time, this is the y2 value at t equal to 10. So for that, another thing you can do is, you know what is the t and y that you observe, right? T and y you already have it here. Okay. T is here and correspondingly you have the y value where the first column corresponds to y1 and the second column corresponds to y2. So from the y2, so basically from the this y array, if you take the nth row and the second column, you will be getting the last entry of y2. So this value. Okay, that is the last row. The second column will give you y2. That will be corresponding to t equal to 10. So I've just printed it here. And the final answer I'm getting is 0.03097. So that is the value of y2. So from the options, it will be 0.03. Yeah, that is option B. I hope this is clear. Now moving on to the next question. Like if you have any doubts, please to stop me or you can unmute yourself and ask. Okay. So moving on to the next question. Solution of the initial value problem ODE, you have given an equation dy by dx is equal to y0 is equal to 0, y0 is equal to -1. So you have to tell, you have to, by using your hand, just integrate it. Okay, manually just do this, integrate it and let me know the answer. I'll discuss the answer. I'll give you like 1 or 2 minutes to do it and then we'll discuss the answer. So the answer is dy by dx, sorry, dy by dx is equal to 10 minus x. So integrating, you will be getting dy is equal to 10 minus x dx. You can integrate both sides. And also remember, so the final answer when you integrate, it will be y is equal to 10x minus x square by 2 plus a integration constant, right? Now we are given when x is equal to 0, sorry, when x is equal to 0, y is equal to -1. So just substitute x is equal to 0, y is equal to -1, which will give you c equal to -1, right? So the final equation will be 10x minus x square by 2 minus 1. That is 10x minus x square by 2 minus 1. So that is option C, right? No, sorry, option D. 10x minus x square by 2 minus 1. Option D is the answer. I hope you got this. Okay, now it's a long numerical question, but it's easy to solve. I'll just explain the question to you first. On mechanism of deactivation of solid catalyst by a parallel reaction in which reactant produces a single product which deposits on a catalyst surface and deactivates it. In a catalyst bed, the rate of equations of reaction of catalyst deactivation. So basically, there are two equations, one corresponding to the concentration, and other corresponding to the activity. So A is the activity of the catalyst pellet, and the C is the concentration of reactant. You have two equations given here. K1 is a modified reaction rate constant. So K1 value is given, K2 value is given. K2 corresponds to the catalyst reactivation. So basically, there are two equations that is given to you, one corresponding to concentration, other corresponding to reactants. All the K1, K2 constants have been given to you. What's the initial condition of the system? At t equal to 0, there it is said that C is equal to 100, A, activation is equal to 1. Now we need to find at value t equal to 5, what are the values of both C and A. And truncate your answer. Sorry, we have to find what is the value of A at t equal to 5 minutes. Truncate your answer to the truncate your answer to 3 places after decimal. Okay, so this question has a lot of writing part. It is very pretty simple when you solve it as an ODE equation. So I'll give you 2-3 minutes and then we'll discuss the answer. I'll quickly show the MATLAB answers. Just a second. So here you have your K1 value given, K2 value given, initial C0 is 100, initial A0 is 1, and we have to run it for 5 hours. Okay, sorry, 5 minutes it has been given. Remember in all your equations, sorry, I'll just show the question once more. We have to run for 5 minutes. But if you remember, see here K1, the value is given in hours. Okay, so the equations, every variable is given per hour. So this minutes has to be converted into hour. Only then you will get the right answer. Otherwise, there will be a problem with units. First, let's do that. This 5 minutes, let's convert into hours. Now we have the equations. I've just directly written the equations here. Okay, or else you can write a separate function and write the equation. That is also perfectly fine. I've written an equation here like this. It is a column vector of the first equation and the second equation. That is a ODE fund. It's an anonymous equation that is written here. Then I'm calling the ODE 45, ODE fund. I'm running from 0 to 5 minutes, 5 where 5 minutes is converted into hours. C0, A0, initial concentrations has been given. Then what I do, I need to extract the results. Okay, the out of Y, the first column will give me C, and the second column will give me A. That's what I do. All rows, first column, all rows, second column. And out of that, I need to find what is the value of A at 5 minutes. That is at the last value of A. So for that, what I do, I print it and I print the last value of A. A, end means it will give you the last end, last index. What is the value of A? Now let me just run this. So finally, I'll get a t equal to 5 minutes. A value is equal to 0.002. Is this clear? Any doubts in this? So this is a different way in which you can write your function. Instead of writing a separate function, maybe you can write an anonymous function. That anonymous function, but see, this is only suggested when you have a very, very simple equations. When you have complicated equations and when you have like many coupled ODE equations, always better that you write it as a separate function. Otherwise, you'll tend to make mistakes. So this is the ODE function here. And here it is point solved. And your final answer, the value of A at t equal to 5 minutes is 0.02. And this is, I hope there is no confusion here. Maybe I can show the full code once again. This is the full code. Now again, moving on to the next question. You have your dCB2 by dt. You have the equation that is given. One of the mass balance equations of the first order reaction, A giving B with 2 CSTR in series, which is basically the problem we have discussed. What kind of problem is this? Is it an initial value problem, boundary value problem, both or none of the above? So the answer is pretty clear. The answer is it's an initial value problem. That's what we have been trying to solve this entire session. So this is an ODE IBP problem. Okay. Now moving on to the next question. This also you have to solve it in MATLAB. It's a transient behavior of a system. You have given two ODEs where epsilon, gamma, everything is a constant. So you have given the values respectively. Initial condition of y is 1, initial value of y is 1, and initial value of z is 0. You need to understand how z is varying with respect to time. for t equal to 0 to 10. So t span is given to you, initial value is given to you, you have to use ODE 15 years. I'll just quickly give you 1 or 2 minutes and then we'll discuss the answer. Due to time constraints, I'll just discuss the answer. So here epsilon initial value is 0.1, 0.01, gamma is equal to 5. Initial value is 1, 0, and T span is also 0 till 1. Okay. We have writing the ODE fund just like we did for the previous example. You're writing as anonymous function because there are just two equations. I'm using ODE 15 years, ODE fund, T span is given 0, 1, y0 is given to me as 1, comma 0. Now I extract the equations out of the solution. The first column corresponds to capital Y. Second column corresponds to capital Z. Okay, so that is basically Y and Z. I'm trying to plot it here, T versus Y and T versus Z. Now what I have to do is I have to identify if the Z value is continuously decreasing or it is increasing or it is increasing and then decreasing. Okay, there are different ways in which Z behaves. First, let me just, you can visually also observe it. So for that, first I'll run that section. Okay, first I'll just run the first part. Only the section I'll run. Sorry. This is a behavior that I'm observing. So if you see here, y is your blue one, z is your red one. So actually z is increasing and then it is decreasing. Either just by visually observing, you can confirm that that is the behavior of z is first it increases. It is a maximum value and then it increases. Then it decreases. Otherwise, if you want to find out from by coding it, this is how you do it. Just like we did before, what you can do is you can differentiate. You can find the differentiation of z, okay? And differentiation of z, you can find out if this is keeps on increasing, what happens? If it is always greater than 0, it means that z value is increasing throughout. If it is always less than 0, which means it is decreasing, okay? Positive or negative side, depending on that. Okay, here you don't have to find dt because you know the difference in time is always going to be positive, okay? So that will not change the sign of sign of how the z is increasing or decreasing. So here we don't want to observe the quantitative value of it. You just want to understand qualitatively is it decreasing or increasing. So just differentiation of z is fine because differentiation of t will also always give you positive value. So if it is always greater than 0, which means the z is always increasing. If it is always less than 0, it means the z is always decreasing. Or else if it doesn't have this always positive or always negative value, then it means that it increases first or decreases first. It could be opposite also, okay? It could be decreasing first or increasing first. If you want to even make sure that this exactly this condition happens, again, you can write some of the if statements, okay? Otherwise, it's easier to just observe the plot and then answer the question. So I'll just run the whole section. So the answer is Z is increases first and then it decreases. Okay. So I'll just show the answers. So Z increases in the beginning and then decreases. This is the answer, option A. Okay. Now, as per the analysis done in the lectures, which of the cases the steady state for A reaches fastest if conditions remain unchanged? Should we go back? K equal to 0. We studied for K equal to 0.5, 0.1, and let me just go back. Okay. Which case A reaches steady state faster. Okay, for different values of K, here the steady state was reached at maybe 20. Okay, here steady state doesn't reach even at 20. Here it takes even more time actually. So what I understand is steady state is reached as a lower K. Is it right? I'm not sure. Let's just look at what the answer is. Because this plot is only till k equal to 20, t equal to 20, right? Basically, if you had plotted some time equal to 60, then you would have got a better understanding. But I'll just give you the answer right now. The answer is okay. Yeah, whatever we've got is right. It's 0.05. That the steady state is reached faster when there is a lower k. Okay, 0.05. Okay, so that's what we observe. Again, you have a simple ODE equation. It's all using ODE 45. I can quickly show you the answer because everything remains the same. Sorry, this has to be not repeating. We have to find z at t equal to 10. I'll just show you the answer right now. You have the initial condition of z and x, t span from 0 to 10. I'm writing the equations as a column vector here for the two equations. ODE fun, t span is given, initial condition is given. I extract the x values as the initial first column, all rows, and y as first column, second column, all rows. And what I need to write is at t equal to 10, what is x? So 10 was our last value, basically, last time value. So what you have to do is from the x, you have to extract the last value, that is x end. So basically, you will be getting at t equal to 10, your x is 2.27 e raised to minus 0.04 or 10 raised to minus 0.04. So that is your first answer, 2.275 10 raised to minus 4. Option A. I hope you got it. I'll share you the recordings and the PPT so that it's easier for you to understand. Again, the next question is identify the correct statement. That is two CSTRs connected in series with the reaction order that is given to you. Okay, now the initial concentration of species are 0. What happens? Concentration of A suddenly increases while there is a lag in the concentration of B, which is correct. Concentration of A and B equally starts increasing and saturate at the same level. No, it's not true. Will be a lag in rise of A, sudden increase in B. Okay. Basically, what happens? There will be a concentration. This is what we observe. There is a concentration of A increases suddenly. But what happens? There is a lag in concentration of B. This I've already explained while explaining the graphs. Please go back to the graphs and refer to it again so that you'll understand this option is correct. Now there's another ODE solver. I'll quickly go and show this code in MATLAB. We have two ODEs. Initial conditions are given as 1, 0.1. We need to identify what the y1 value is. Basically, y1 value is at x is equal to 100. And you should use ODE 15 years. I'll quickly show you the answer. So you have the, I'll also close all. Okay. Your initial value is y1 is 1 and y2 is 0.1. Expand, you're doing it for 0 to 100. Okay. And this is your ODE fun, your first equation in the first row and the second equation in the second row, forming a column vector. And then I'm using ODE in 15 years as given to me in the question. I write ODE fun, expand I have from 0 to 100. I have the initial values that is given here, which is 1 and 0.1. I run the ODE solver. From the x, I extract the y1 value, which is the first column, y2 value, which is the second column. And what I need is I want the y1 value to be y1 value at x is equal to 100, expand equal to 100, basically the last value, but rounded off integer. So for that, what I do, I use the inbuilt MATLAB command round, and from y1, I take the last entry. Okay. So when I run this, this is what I get. Okay, I get the y1 value is actually 0. Okay, you can plot this and confirm if this answer is right. But basically what happens is your y1 at x is equal to 0, x is equal to 100 is 0. This is the nearest integer to it. Basically, if y1 value, if I take, this is what I get. It decreases from 1. It's slow. If you can see, it slowly decreases. An exact value is 1.141 e raised to minus 11. Rounding off to the nearest integer, I'll be getting it as 0. I hope this is clear. You can try plotting this y1 and y2 so that visually also you can confirm this answer is right. Now moving on to the last question. This might be a little bit tricky because this is not similar to what we have tried solving this week. I'll just read the question for you quickly. You have three reactions. A giving B, it's a slow reaction with a rate constant K1. And 2B giving C plus B, again a fast reaction with rate constant K2. And then you have a reaction B plus C giving A plus C. Okay, you don't have to worry about these reactions. There are three reactions that is given to you. So reaction equations for CA, CB, and CC. How the reaction is varying. You have the initial conditions at T equal to 0, CA equal to 1, CB is equal to 0, C is equal to 0. K1, K2, K3 is also been given to you. To analyze the stiffness at T equal to 0, choose the correct two norm of the Jacobian matrix. So basically, I need to calculate the Jacobian matrix and the norm of it. What is Jacobian matrix? For the people who don't know, I'll tell you. Jacobian matrix is the matrix of gradients. Okay. So you have the three equations. On these three equations, you have to calculate the gradient. Okay, so that will be the first equations, Jacobian for you if it is not clear. There is an inbuilt MATLAB command for Jacobian. I'll just show that to you. And mathematically, what Jacobian means is it's a matrix of gradients. If you want to know more about it, you can just go Google it and see. See, Jacobian matrix computes the Jacobian of the scalar of vector f with respect to x. So if you have an equation like this is how you write the Jacobian function. You write the variables that is there. Okay. Here my variables are x, y, z, u, v, and I have write equations. So this is my first equation. This is my second equation, and this is my third equations. And this is a variable with respect to which I have to calculate the gradient. So it will come as dou by dou, d by dx, d by dy, d by d, sorry, not actually d by dy. Here will all be partial derivatives. So it will be dou by dou x, dou by dou y, and dou by dou z. You have three equations and three variables that is, okay? And this returns like this, okay? This will be the first equation derivative with respect to x. So that is y z. And this next will be first equation derivative with respect to y. That is this zx. And the first equation derivative with respect to z, which is the xy. And the next is this second equation's derivative with respect to x, y, and z. This is the third equation's derivative with respect to x, y, and z. This is what Jacobian calculates. Okay, you can maybe take this equation, try to solve it manually, and try to compare if the answer is right. Okay, so first you have to compute the Jacobian, and then it is set that t equal to 1. Okay, and then you compute the Jacobian at that t equal to 1, and then you calculate the norm of it. So that's what we are intending here. So this is the code for it. Okay. So first what I do is I write all the reaction rate constant K1, K2, K3, what is given to me. Initial concentration Ca, Cb, C0 is also given to me. I write the three equations. Okay, so this is the first equation. This is the second equation. This is the third equation. Remember, you have to write it in terms of variables. Okay. Now what I do is I write, remember in the Jacobian, you have to write a symbolic variables. So here symbolic variables, that is S by MS, CA, CB, CC. This is what I am trying to find the derivative with respect to. Here variables, instead of X, Y, Z that we saw earlier, here my variables are CA, CB, CC. And now these are my functions. This is my first equation. This is my second equation. And this is my third equation. Okay. Now what I do is I need to find the Jacobian. How do I find the Jacobian? The f, this is the function that I'm trying to find the Jacobian, and these are the variables with respect to which I'm trying to find the Jacobian. Okay. Are you done with that? Actually, this part was not necessary. Okay, I'm sorry for that. This part is not necessary. We're not using it anywhere. Okay, till here, I'll just show you what the Jacobian looks like. Let me just run this section. And let me just show you what J looks like. Okay, J is a symbolic thing. See, it is 1 by 20, the symbolic equation. See, it's a function of CC. This is a function of CB. Likewise, you will be getting a symbolic Jacobian. This Jacobian is still, it is a function of something. Okay, it is not scalar values. It's still a function of something. Now we need to substitute values for CA, CB, CC so that you get the Jacobian, which is a matrix of scalars. Now from functions, you have to convert into scalars. So for that, you can use the inbuilt MATLAB function, which is subs. Okay. In that, what you do is, in the Jacobian, you're telling the actual variable is CA, CB, CC. With that, you substitute capital CA, CB, CC. That is this values. Substitute this value instead. This is because when the system begins at T equal to 1, this is the concentrations, right? So what I'm telling is, here the variables are there, right? Sorry, the variables are here. As I said, CC is a variable. Now, instead of this CC, which is a variable, substitute the actual value that is given here, CC. So that's what subs does, substitute. In J equation, for this variable, substitute this values. Okay, the syntax is very important. Please keep a note of it. Then you will get a scalar J0. I'll just run this for you. And see, J0 is a scalar matrix. J was a symbolic matrix. And here J0 is a scalar matrix. Now we need to find norm. So for norm, also I'll do help norm. See, and if you just keep norm b comma 2, you will be getting 2 norm or the Euclidean norm. Even if you don't give 2 also, by default, it is going to calculate a 2 norm or the Euclidean norm. Okay, so here what is asked is to calculate 2 norm of the Jacobian. So I calculate J0, I give comma 2. Okay, so this is my answer. And I finally display this answer here. So running, I'll get Jacobian at initial condition is this, and the norm is 7.07 e raised to minus 0.2. So I've also given the options here. So that will be, is this one, right? C, answer C actually. 7.0 something, 10 raised to minus 0.2. So it will be the option C. Again, sorry, in this question, there are some unnecessary parts that have been written. I'll just remove that. Sorry, not this one. This F1, F2, F3. This was not required actually. Okay, I'll just run again and show it to you. See, Jacobian at the initial condition, and then this is the actual value, norm of it. I hope this is clear. If you have any doubts, please to ask. Okay, we've already gone beyond 8 p.m. So if there are no doubts, I'll be ending the session. Thank you so much for attending. From next week onwards, it will be same. We'll be back to our original timing, that is Fridays, 6 to 8 p.m. Please join the session. And this week's recording, I'll be trying to upload it as soon as possible, both the recording and the PPT which has been showing to you. Thank you so much for attending the session. I'll be ending the session soon.